It is on its way. It is gone. It has left my facility.
And the webinar has started, everybody.
Thanks a lot, Tony.
Participants are trickling in, and I will send a message to everybody about using the Q&A. Thanks.
Thanks a lot, Tony.
Okay, so
Yep. Full screen mode down below, a little bit further down, David. Right there.
All right, looks like we got a good group of attendees already lining up, and we are 2 to 3 minutes after the top of the hour. Maybe we should get started. Greetings, everyone, and welcome to our iGuide webinar series today. And I'm so delighted to see all of you are here, and thank you very much for joining. I'm Xiaowen Wang at the University of Illinois, Urbana-Champaign. iGuide stands for Institute for Geospatial Understanding through Integrative Discovering Environment, in short, iGuide, which is one of the NSF-funded Harnessing the Data Revolution institutes. And I'm serving as the director of NSF iGuide, and it's my huge pleasure to introduce to you my colleague, Dr. Dave Tarbolton at the Utah State University, who's a professor of civil and environmental engineering there, as well as the director of Utah Water Research Laboratory. Most relevantly for today's webinar, Dave is serving as a co-PI and co-lead of our convergent science catalyst team as part of iGuide. So invite Dave to introduce our speaker today. Thank you very much, Dave.
thank you, Xiaowen, and it's my pleasure to introduce Fred Ogden, who is the chief scientist in the NOAA National Weather Center Office of Water Prediction in Tuscaloosa, Alabama. Prior to joining the National Water Center, he had an academic career at the University of Wyoming, and prior to that, at University of Connecticut. While at the University of Wyoming, he and I collaborated on the CI water project. And it's really exciting to see the evolution of hydrologic modeling that Fred will be sharing with us today. iGuide is all about geospatial and geospatial understanding. And I think distributed hydrologic models have a big role to play in that, as well as the whole geospatial fabric that connects the water infrastructure of the country, the water data infrastructure. So it's my pleasure to welcome Fred and let him tell us about the next generation of water resources modeling and innovation at the intersection of hydrologic, computer, and data sciences. Thank you, Fred.
Thanks, David. Can everybody hear me okay? Excellent. Let's go to the next slide, please. The National Water Center, it's a relatively new federal activity. It's aimed by law to be a place of collaboration between federal water prediction agencies. And I won't read the mission statement and vision there, but it's we're now about 140 some staff members. It will become quite a large, many contractors, about 40 federal employees and about 100 contractors. Next slide, please. The National Water Model, for those of you who remember, was or those of you who don't remember, was originally proposed by Quasi back in 2011. It was proposed as a community model. I think David and I were on the board of directors of Quasi at the time. There was a lot of interest between the academic and research communities But ultimately, it lacked agency support because agencies were developing their own models, their own frameworks, and they didn't really see the need for the academic community to come in and say, here, use this. So it kind of withered on the vine. But in 2014, the National Weather Service recognized the potential for making predictions outside of their traditional river forecast center forecast points. David Maiment was heavily involved in that. 2015, the Summer Institute aimed at kind of highlighting the capabilities that existed at the time. And in 2016, the National Water Model version 1.0 was operationalized. And it was based on WRF Hydro, which is NOAA MP land surface model with some added routing functionality and a conceptual groundwater model. And as of 2021, National Water Model version 2.0 has been operationalized over the contiguous United States, Hawaii, Puerto Rico, US Virgin Islands, and we're heading for portions of Alaska. It's not quite operationalized yet, but we're almost there. Next slide, please. The National Water Model, the blue lines on this map show the rivers that are covered by river forecast centers. The red lines show the National Hydrography data set. And you can see the difference. We go from about 110,000 river miles to over 3.4 million river miles of forecast capability. So it represents, at least for the continental US, a significant increase in capability. Next slide, please. Now, the current operational National Water Model, it applies a homogeneous formulation over the entire continent. NOAA MP running on a 1 kilometer grid. Now, NOAA MP, mind you, was developed for coupling land surface to climate models. It was developed for large scale applications. It does not resolve the topography. And actually, if you look at the NOAA MP code, it doesn't, the land surface slope and aspect do not appear in the code. The runoff that's predicted, either lateral flow or surface flow, is routed on a 250 meter grid. That's the top center and top right box. Water is allowed to percolate out of the soil. It's limited in some cases by calibration, but it goes into a conceptual nonlinear reservoir. Those combined sources of storm flow generation go into a vector-based Muskingum-Coons routing network. And we, over the last couple of years, have added basic water management and used incorporated reservoir release data where available. Next slide. When we look at how the National Water Model performs, the Weather Service, our priority right now is producing inundated area maps based on forecast stream flows for the entire NHD network. And if you look at how it's performing, inundated area is very highly correlated with peak flow discharge estimates. If you look at how the National Water Model operationally is performing in terms of peak discharge, this is an analysis of the Water Model version 2.0 retrospective simulation. On this plot, bigger dots are better. Those are points where, in the median sense, the peak discharge error is within 25% of the observation. And the violin plot shows the distribution of peak discharge error in the median sense across the entire network. So you can see that the current formulation seems to perform better in wetter, cooler climates. You can see Pacific Northwest, Northern Rockies, and some points up in, say, Northern Michigan. In the rest of the country, 50% of the time or more, the peak discharge error is greater than, the absolute peak discharge error is greater than 25%. So we can conclude that the performance of the National Water Model varies regionally. Next slide. Now, we have OWP, the Office of Water Prediction, has a community advisory committee for water prediction. And in 2019, the last time we met in person, the report made some recommendations. And one is to articulate the requirements for further development of the National Water Model, place an emphasis on improvement for observational data and potential emphasis on improving data assimilation techniques and processes, And then to stand up a community development engagement process, governance, and center, pursue proven mechanisms for community adoption. And that's what we've been focusing on since about 2019. Next slide. The General Services Administration of the United States government has a group of computer science Ph.D. rotators called 18F group. They did an audit of the National Water Model code base, and they made some very important recommendations. And I'm going to draw your attention to number 4. If we go to the next slide, if we treat our interfaces as products, that means it's really important for modularization and flexibility. As we've tried to modernize, modularize the NOAA MP code to swap out components and test alternative solvers for different fluxes and states. We found that the research nature of that code and the fact that it's evolved over about 20 some years, there's a lot of legacy stuff in that code. You'll find variables that are passed down many layers of subroutines deep and then set to a constant, for instance. It became clear that to make advances, we might want to consider rewriting the entire code. And that's largely what these recommendations said from the 18F audit. Next slide. The purposes of the National Water Model are protection of life and property, for emergency management, flooding, for predicting inundated area and the occurrence and duration, drought, dam reservoir operations, water quality, as in contaminant spills, nutrients, water temperature as they affect habitat, et cetera. Commercial interest, power generation, fisheries, agricultural, and other industries that rely on our forecast. You could think of water supply companies, irrigation companies, insurance companies, and others. Next slide, please. The challenge in continental scale hydrology is one of predictability, process, and parameters. I'm not going to spend a lot of time on this. There's a presentation that I gave at AGU earlier this year that Quasi's posted a copy online if you want to learn more about this figure. But the problem is, if you look in the center of this figure where hydrology is dominated by the soil, many things are important that are very low observability. Layering, anthropogenic effects, macropores, transient phenomena, heterogeneity, seasonality, freeze thaw, bioturbation, shrink swell cracking. To describe those processes in any kind of physically based way requires an enormous number of parameters, and the predictability suffers for that reason. At the end members of this figure, infiltration excess and saturation excess, we have good theory. We have simple models that actually do pretty well, but we lack a general theory of storm flow generation. And that is a real problem in terms of the environmental prediction problem in general. Next slide, please. This picture shows a great example of soil-dominated hydrology. This is a photograph taken in Iowa after an April thunderstorm. Same slope, same land use, same aspect, same soil type, same everything. But look at the difference in behavior depending on just how the farmers, what practices the farmers use to till their ground. That looks like an intractable problem to me. So coming up with flexible ways to try to model things and see what works best from a hydrologic standpoint. Next slide, please. So the water prediction challenge is significant. Hydrologic science does not have a comprehensive theory of runoff generation. There's no universally applicable hydrologic model. Water prediction progress will come from hypothesis testing in a common environment that employs fair, standards-based and open source data, methods, and models. That's I think, a very sophisticated view of the state of the problem. Next slide, please. Now, the need to advance water prediction comes, at least from the federal perspective, from several different angles. One is federal agencies struggle with model selection, identifiability, and interoperability. Every agency has its own models. They all come with their own data model. They don't play well together. The second bullet, legacy codes and heterogeneous computing environments impede advances. We've got codes written in Fortran, and Python and C and R and you name it. Finally, the contemporary open source software paradigm encourages collaboration, evidence-based model and module selection, and promotes interoperability. So how far can we take this concept? Let's go to the next slide. The proposed solution that Office of Water Prediction has arrived at is to develop a computational framework that allows arbitrary methods and models to calculate fluxes of interest and integrate them over arbitrary timescales and control volumes in an environment that will appeal to domain scientists using contemporary open source software development methods to provide maximum flexibility, ease model interoperability, allow evidence-based evaluation of different approaches, and take advantage of each agency's considerable experience. So if we can focus on the models and how they work and how to improve them, rather than struggling with issues related to all of this diversity that exists, if we can eliminate, if we can stop having to develop a new data model every time we develop a new model, that would be fantastic. Next slide, please. The enabling technologies and standards for this effort come from computer science and engineering, geoscience, data and standards, and from hydrologic science and engineering. On the computer science side, GitHub and the basic model interface provide an environment and a standard for model coupling that actually, frankly, those things were not in wide use back in 2011 when the National Water Model was first proposed. In terms of geoscience data standards, WaterML 2.0 provides the high features data model, which describes the hydrologic landscape. We've also got a lot of experience with big data, machine learning, et cetera, that we can bring to bear on this problem. Particular situations where they've been shown to be valuable. We cannot dismiss anything out of hand. The flip side of that is we don't need to a priori assume that a particular formulation will be optimal in a particular setting. So if we think about this diversity of formulations, there might be a place for everyone. A point where machine learning might work well there as well. You might be able to get others of these to work there, but if you're interested in getting something approximating the right answer for the right reason, you might want to consider allowing a diversity of models in different places. Next slide, please. The Nextgen modeling framework requirements were the outcomes of a joint NOAA, U.S. Army Corps of Engineers, Audit, USGS, and U.S. Bureau of Reclamation requirements workshop in October of 2020. And we required that this framework be model agnostic with maximum flexibility so that as models, data sources, and needs can change, the framework can accept those changes. We'd like a common architecture to avoid duplication and promote interoperability. We'd like open source development to promote code reuse and development efficiency, provide an authoritative repository for federal water models, and ease and encourage participation by partners in the community. We'd like to apply standards where applicable for coding and coupling, data and metadata, model verification, validation, and test data. And above all, we'd like it to be friendly to domain scientists and engineers. You shouldn't have to have a degree in computer science to interact with the framework. You shouldn't have to entirely rewrite your code. If you can adapt your code to be compliant with the BMI standard, it should work with this framework. Slide. The objectives: we want to engage the community using open source, standards-based. We would like to provide well-documented examples, model agnostic focus on interoperability. We'd like it to link with NOAA and other weather and climate models, ease scientific evaluation of coupled models and methods, running on hardware from laptops to supercomputer, and then have a domain science or engineer-friendly coupling interface. We've established a target of 2 weeks for a domain science or engineering graduate student or new employee to add functionality to the framework. Next slide. Okay, we are data model centered. A lot of proposed networks are solver centric. Solver centric, David Tarbot and I have had discussions about this. They don't scale well. And the problem in hydrology is we oftentimes, you know, the ocean is the ocean, the atmosphere is the atmosphere is the atmosphere, but watersheds are the soil, the rock, the trees, the worms, the farmer, everything that's happening on them. Solver-centric solutions do not scale well because we often are not dealing with a continuum in the hydrologic modeling domain. Let's go to the next slide. So we take this landscape and we break it up into elements based on the WaterML high features data model, which is centered on some concepts: catchment, flow path, water body, and nexus. Those four components provide the skeleton, which we can start to describe a common hydrofabric. How you discretize the catchments, what their size. Data, on the other hand, provide the comprehensive or unifying organizing principle that these models interact with. So as this figure is shown, the different shades of green are different catchments that have been delineated using some program at a scale that someone thinks is an appropriate scale. Maybe some parts have been merged to make them, to eliminate small little catchments. But as you can see, you can create something that very much looks like a graph or a tree out of this organization. Just to be clear, a catchment is an area of the land surface that has hydrologic processes acting on it. A flow path is, you can think of that as a 1D kind of a routing connector where you might apply a 1D flow routing method. A water body is a 2 or 3D object that occupies space in the landscape, significant area. You could apply a different model to that. For instance, in this figure, we've got a reservoir and then we have an estuary downstream from it. And then they're connected by what are called nexuses. And a nexus is basically an internal boundary condition that describes how these things interact with each other. Next slide. You know, as I said before, the federal partners, we had in January of 2021, we had a workshop to discuss model coupling. And we invited EPA and Army Corps, USGS, ourselves, Bureau of Reclamation. And we talked about the different methods that are out there. And the EPA, you know, or excuse me, the Department of Energy, who attended this meeting, they have done a lot of work in this area. But when we think about a data-centric coupling, a data-centric framework where models are not necessarily tightly coupled, the basic model interface becomes apparent to rise to the top. We have extended it to allow, the basic model interface did not originally envision operation on a supercomputer environment. We've extended the standard to allow that in a little bit of a simplistic way, but we've added a functionality to write out a model's serialized state. We have a BMI command that essentially tells a model, stop and save your state to a file or in memory. After it's done and reports that it's done with that, then all of that entire state can be moved to a different part of a machine and restarted. That allows for checkpointing and it allows for load balancing at the model level. We've also proposed another addition, which addition to model units, et cetera, we've defined a role variable. We'd like to know, when we ask a model to tell us what its variables are, we'd like to know if it's a parameter or if it's a state variable, is it something that we can calibrate, et cetera. So there's a minor addition to the BMI standard. Next slide, please. In terms of the data model and process level complexity, if we want to test different modules of process calculations, It's simple for a conceptual model, such as the one shown on the left. When you start talking about a fully distributed model, like the one on the right, it becomes really difficult. So we recognize that that is a problem, but thinking about this in this way of coupling modules starts to open up the door towards creating and testing different hydrologic model formulations on the fly. Next slide. One of the strengths of the framework is that we can add and test complexity. Looking at the middle of that figure, we can start out with a simple lumped model where we would apply uniform forcing and have one, say, geomorphic instantaneous unit hydrograph to route the water. We could then go to a tiled approach where we simulate different land covers separately. They don't interact, but they give a different response. We still have one geomorphic instantaneous unit hydrograph. Then we could add complexity where we go to semi-distributed, but it's still lumped with uniform forcing, where we might have different soil land use complexes, like that stuff along the bottom row, which show how you might calculate those. And each one of those dominant soil land use complexes might have its own GIUH. And then finally, we could get to a place where we're using that semi-distributed model with distributed forcing, and that increases the complexity further. But the cool thing is, we're building all of this off a common set of underlying hydrography, topography, land surface data that we call the hydrofabric. And I'm going to talk about that for the rest of the presentation. Next slide, please. What is a hydrofabric? Now, we've developed a terms of reference document at OWP because we have a diverse set of computer scientists, domain scientists working on this project, and we all use the same terms in different ways. It's something we really struggle with as a large interdisciplinary agency. So we've started this terms of reference, and here are some basic definitions. Hydrofabric is a geo-referenced digital representation of the hydrologic features of a region. It may include topographical catchments derived from a digital elevation model, stream vectors, water bodies, etc., or spatially varied land surface properties related to land cover, soils, vegetation type, etc., or derived properties such as topographic wetness index or other indices used to assign parameters for modeling. Hydrofeatures are physiographic properties of a hydrologic landscape describing or affecting the movement of water across or through the earth. A hydrologic feature is defined in the WaterML standard as an object of a type defined in the hydrology domain whose identity can be maintained and tracked through a processing chain or workflow from measurement to distribution of hydrologic information. And then the hydrologic landscape is assumed regions of the earth having similar climate, soils, underlying geology, topography, vegetation, and history. Two different parts of the earth that lie in similar hydrologic landscapes may be assumed to behave hydrologically similar. It's useful for regionalization of hydrologic model formulations and their parameters. So I just wanted to get that out of the way. Next slide. We have four components of a hydrofabric. The blue line features are flow lines and per flow line catchment geometries. The flow line catchment topologies, how are they connected? The attributes to support routing and rainfall runoff modeling, and the software and data models to make the creation of these open, reproducible, and flexible. So I'll remind you, we're trying to work towards getting out of the business of every model having to come with a new data model. Next slide. So we can define the computational elements, which would, as you could imagine, require some optimization and some assumptions about dominant processes. We can link together space-time processing so the modular elements can act as a whole. We can provide Earth system attributes for model execution. We're model agnostic, right? We can apply any kind of model we'd like. We'd like metadata to support and enhance the data assimilation. And we'd like to move towards cloud native data formats and structures to support analysis over large scales. Next slide. To produce the hydrofabric, we start with baseline data. And the baseline data are the data that you would download from an agency site. It's the best, it's the authoritative data source. Think the National Elevation data set, think National Land Cover data set, any of those kinds of data sets. Now, they're usually not NHD plus, NHD flow lines, they're not optimal for a computational network. The NHD plus has a lot of really small reaches that are formed by near adjacent junctions of tributaries coming into a main stem. And those little small computational reaches are not optimal for computation. So we want to refactor those. And the first thing that we do is we refactor them based on flow line length criteria. And we do it in a way that doesn't lose network resolution. It adjusts the flow lines and then the catchments, because we, in the National Water Model context, require correspondence between catchment and flow line IDs. So if we have a short reach of a channel and we want to eliminate that, we could snap the junction to eliminate that reach, or we could extend the length of one channel just a little bit to make it come in at a common point. And then finally, we can set up for modeling tasks. The USGS has their own set of modeling tasks in terms of NOAA Nextgen National Water Model. We aggregate to a common catchment size distribution, and then we build release files that describe the topography and the hydrogeography of the new region. Next slide, please. The new national data product that the USGS is producing consists of a nationally consistent and authoritative reference fabric to make sure that the I think that's computational. I can't read that word. My figure got smunched down there. The elements are topologically correct, so the water flows where it should, geometrically correct, so space is represented as it should be. If we merge basins, if we have to get rid of a tiny catchment, we merge it with a bigger neighbor and we preserve area in that way. And then hydrologically correct so that the headwaters start where they should. And this work is being led by David Blodgett and the group at the USGS and Mike Johnson, who's working with us on this project. And you can see there's a lot of different partners involved at the bottom of this slide. Next slide. From the National Data Project to making it next-gen ready for the water model, we make sure the computational elements represent the scale of the process being modeled. The current operational national water model has over 500,000 catchments that are much less than 1 square kilometer. And those are relics of this, of the hydrofabric. We have written code that splits large or long catchments and flow paths into a more uniform size. We've collapsed flow lines and catchments that are less than a stable routing length, so we don't require really small time step in our routing for current stability purposes. Aggregating small catchments to scales representative of the physical processes being modeled, which that's a mouthful. Do we know what that is right now? Not exactly, but all hydrology, like politics used to be, is local. Once the water's in the river, what produced it doesn't matter anymore. And that's something that I was talking, Vitek Krajewski told me about at a conference last week. And that's a good point. It's really a small scale, square kilometers type of scale process that we're really interested in getting right in the context of the National Water Model. Let's go to the next slide. How am I doing on time? I'm doing fine. So we have attribute-rich workflows. Now, these are really important. We would like to have a workflow that maintains provenance back to the original underlying base data. And that's a really important consideration when you think about reproducibility. Mike Johnson, developed this slide for me. He's designing open source data catalogs and efficient processing tools. There are currently about 15,000 data sets that can be accessed through this open DAP catalog. So far, we have routines that mirror the CAMELS data set and those needed for most current OWP model, OWP supported model formulations. So we're making use of public domain, free, accessible data where possible. Next slide. The code is modular. Most of these processing tools are being developed in R. A good example is that figure I show at the bottom right there. It's called the high catchment aggregate function. Because the catchment size distribution in the NHD plus is not an optimal computational domain, we developed this tool to allow us to aggregate and make it the size that we want to test. The Hydrofabric package, it says here, is an opinionated collection of packages designed for disparate hydrologic modeling tasks. All packages share an underlying design philosophy, grammar, and data structures. And if you look at the NOAA OWP GitHub page, and I'll give you a link at the end under Hydrofabric, all of those tools are there. And there's, in gray, there's a list of what some of those tools are. There's one for network manipulation, network refactoring, network aggregation, data releases running elected subroutines, one for accessing remote data resources for parameter estimation, rapid catchment parameter summaries, and for accessing Army Corps bathymetry data and embedding it into a DEM for extracting cross sections. So that's just an example of the tools we've developed so far. You might want to consider looking at those. Next slide, please. The motivation and direction. The national hydrologic efforts from USGS and NOAA are moving towards the creation of massive data. The Hydrofabric is what organized the velocity needed to answer real-time water resources questions and gain community momentum. It does so in a way that each piece, the flow line, catchment, and code, is individual, but also a coherent and consistent part of the larger whole. And it supports model-agnostic operations by maintaining provenance to underlying data layers, which eases reinterpretation of the data. Because we don't know a priori which model to use when and where, we want to be able to rapidly test and prototype and evaluate different model formulations to try to come up with something that's approaching some kind of an optimal representation of the hydrology acting on the hydrofabric. Uh-oh, my screen is frozen. There we go. Why is the hydrofabric concept useful? It facilitates environmental data science. It's fundamental to discretized and any flavor of hydrologic modeling. If you want to use any formulation, you can start with the common hydrofabric. It supports efficient data dissemination and use. It provides interoperability between disparate modeling tasks and allows the aims of the Nextgen Hydrologic Water Modeling Framework to take advantage of advances in other domains like data science, cloud-based spatial analysis, etc. Next slide. The community engagement. So everything we're doing is on GitHub, as opposed to, the National Weather Service has taken a run at community-based modeling several times. But for instance, the Community Hydrologic Prediction System, CHIPS, did not use GitHub. GitHub didn't exist when it was proposed. We're taking advantage of what other fields have learned about open source development. We're unifying data models to promote code interoperability so we can stop inventing data models. By sharing code, we can prevent bug reinvention. How many times do we have to write Penman-Monteith evaluation? And how many times do we have to fix the bug that somebody makes by misinterpreting the log-law boundary profile, boundary layer equation? We can support a diverse computational environment in terms of hardware and programming languages. Right now, we are using the graph nature of the hydrofabric to break up the computational domain into regions that don't share a lot of information. That minimizes communication on a supercomputer. And it allows you to run this MPI code on a laptop that has the MPI libraries installed or on a supercomputer. And our extension to the BMI standard allows load balancing and checkpointing of models running in this framework. There might be uses for this framework outside of hydrology. Water quality would be one you could think of. And then it allows the federal water prediction community to evaluate models by supporting scientific evaluation and advance demonstrably superior approaches. There are a lot of agency-specific models or academic models. You know, you've probably all seen the paper that showed that people use models and studies that come from their graduate group much more than other models. If we can make it easier to use everybody's model, then we can start comparing many more models together. Next slide, please. So the stage is set for this collaboration. We have a transparent open source code development paradigm, standard geospatial data models and libraries, the CSDMS basic model interface extended to HPC, and it meets the multi-agency need to promote science and interoperability. So the potential for societal impact, you know, is really quite large with this approach, I believe. Next slide, please. I think this is the last slide. Here's the GitHub site. This gets you to the Nextgen Framework page, but at the NOAA OWP level are all the other work products that we've developed. And we welcome contributions from the community. I think that's one of the things that we will depend on as we go forward, as people continue to adopt the standards that we support, and they're widely known standards. Then it makes sense that new model development could happen in that framework and take advantage of everything that it gives you in terms of interacting with, say, commonly available forcing data sets. And there's my email if anyone has any questions or things they want to talk about. And with that, I think I am right on time.
Thank you so much, Fred. That was a wonderful tour through some of your thinking related to this model and the opportunities for connecting with some of the geospatial challenges that are faced, which I think is what our guide is going to face. So yeah, open it up to questions. I see you, at least one has come in through chat, so I'll read it out. From David Maidment. Fred, I heard you say that a goal of the National Water Model is to create inundation mapping across the landscape. How about adding an element for each catchment that is inundation volume, that is volume of water contained in the stream or floodplain within the catchment? We can define the state of this inundation volume and associate that with a map. Then the inundation mapping goal is achieved.
That is a very good point. And the generalized main stems approach that we've kind of settled on for now as being the best way essentially does that, I think. But that's a very good point, David. The one source of uncertainty that I would say is, you know, we don't know. The water in the channel is one thing. The water not on the channel is something that I think is more uncertain. So we'd have to take that into account.
I don't know if you're seeing the questions, but I can read them out here. The next one is from Jack Liu. Great presentation. How does the Nextgen water modeling framework incorporate human activities infrastructure within watersheds nearby and far away, which may have substantial impact on water availability and flows?
To date, it does not. We've been developing it for 2 years. The first year was a prototyping exercise before we settled on the BMI standard. And the last year has been focused on BMI, high features data model, and getting the computer science pieces together. The domain science part of this is not as far advanced, where we're starting out with really simple models, but we envision doing the kinds of things that you're talking about. Anthropogenic effects, that's a really challenging issue, but I think we would call it a low technical readiness level thing, but it's a fantastic set of research questions.
Okay. So from Venkatesh, what skills are needed for students or even current working professionals to be able to contribute to and use this framework? I think you said it was 2 weeks of work.
That's the goal. We support, okay, the framework is written in C++ because it's object oriented. And then my screen just froze. Can you still hear me?
We can.
Okay, great. So C++ is the framework, and we would therefore support models written in C++, but there are not many of those. We do support Fortran, Python, and C. So knowledge of one of those structured programming languages and knowledge of BMI. Those would be that's the bar for entry for a domain scientist, new graduate student, or employee. If you don't know a structured programming language, and if you can't, look at an example of a BMI module and emulate that, that's kind of the limit, I think.
Okay. Another question from Courtney Flint. What is meant by an opinionated collection of packages? I see this on Tidyverse website too. Interesting choice of words. Can you tell us more about this terminology?
I do not know. Those slides were provided to me by Mike Johnson. And I would say, that's probably a David Blodgett term, would be my guess. Sorry, I can't answer your question, but I don't know what that means.
Anybody else on the call want to maybe answer that? Do we have some R Tidyverse users? That's all the questions that we have that have come in through the Q&A. Anybody else with questions for Fred? I have to say, I really like the idea of stopping having to develop a new data model each time we have a new model. So if we can pull that off, that'd be really great. And I think the opportunities for using the sort of hydrofabric that's coming out of the water center to more broadly look at the sort of geospatial problems that are water related in iGuide are probably incredible. So I'm hoping to learn more.
One of the nice developments, the infrastructure and jobs law that was just passed includes, I think NOAA will probably spend nearly $100 million improving the bathymetry data collection, mostly in coastal margins that haven't been measured in, say, 100 years, but also some focus areas in inland bathymetry, because the Army Corps just tends to survey where they dredge, not outside of those areas. And the simple fact is, if we don't know bank full capacity, we have a very difficult problem estimating inundated area from a flood. The other thing that I didn't really mention is the high features data model doesn't specify cross-section data standards, and cross-sections are not enough. We also need a long channel data, such as top of bank, and these need to be 3D georeferenced, top of banks, and also top of other hydraulically important features like embankments, roadways, culverts, bridge openings, and all of those kinds of geometric things that a LiDAR could possibly measure. So one of the things we're struggling with right now is developing a suitable 3D geospatial model for hydraulically relevant features.
What role do you think artificial intelligence might play there? I guess a large part of the iGuide project is artificial intelligence.
I think the potential is enormous. I really do. I think, mining point cloud data to extract hydraulically important features seems like it would be a very fruitful path. Things that don't show up in a DEM, even a 1 meter DEM, could be a roadway, some kind of a flood wall or embankment that's relatively small, but has an important, if it can create an additional foot of backwater that then causes some low spot to overtop and breach, that's an important thing to know.
There's one more question coming out of
There's a question in the chat, or in the is from Rajesh Kalyanam. What is your vision for how BMI would support and/or foster fair science?
That, I think, the BMI standard envisions a master program that interacts with models. And the other thing the standard envisions is that BMI compliant models need not be aware of other BMI compliant models to work in the framework. That is a good thing and a bad thing. It's a good thing in that, you can develop your model to do what you want it to do. If you don't keep in mind that some of its state variables might be overridden at any time, it can probably create some unanticipated consequences. There's an interesting computer science is common. Unit testing on systems of models running in something like a framework is not. That is a need that I think we could partially address your question with coming up with good practices for that.
Yeah, I guess following up on that a little bit, I guess the sort of data repositories communities doing a decent job on findable and accessible, but maybe BMI has a role to play in interoperable if you've got different model components can interoperate, and that would enable reuse. So maybe that's a slightly different take. I don't know.
No, that's a good point, David. I appreciate that. I didn't really answer the question very directly. I got a little sidetracked there. I see another question. What is the incentive for the academic community to engage with federal agency efforts? It appears the incentives are different for the groups. From my perspective, if you look at the history of the original national water model and the fact that when it was presented to the agencies didn't support it, led to a significant, it was a little bit of a disincentive, I think, for development. Now that the agencies want to support it, if you develop something that the agencies can use, the incentive as a researcher is, and I know this from firsthand,
Audios.
Yeah, we
and developer.
We missed much of that audio. I don't know if you want to try again.
Let me turn off my camera and see if that helps. Can you hear me better now?
We can hear you. When you're speaking, we can hear you perfectly, but just occasionally it drops.
Okay. Well, I'll just answer that again. As a model developer, when I was in academia, if an agency decides to adopt your approach, when there's a problem, they come to you for a solution. That's the incentive if you're a developer.
Okay. So a couple more questions now, they're rolling in. You mentioned some of the many different ways that changes in land surface are represented in the models. How are heterogeneities in the inputs, i.e. precipitation, integrated into the model, and what challenges do you see when dealing with finer and finer resolutions?
Oh, that's a really tough question to answer. Right now we're focusing on lumped models because when we refactored the NHD Plus, we specified that we wanted a minimum reach length in channels between channel junctions to be something like 200 meters. And we would like our minimum catchment size to be 3 square kilometers. So that's part of the refactoring process that's necessary to create a computational, hydrofabric that doesn't require either simulating obnoxiously small areas or using really small time steps. What was the rest of the question?
So about heterogeneities in inputs and integrating that into the model and finer resolutions.
Yeah, I mean, the hypothesis is unproven that finer equals better. In fact, I think in many cases, there's something like an optimal resolution, and it probably isn't tiny, because tiny, requires a lot of knowledge. U.S. Department of Energy, for instance, they can model a postage stamp infinitely well, but when you go to a catchment, their models suffer from the same problems that the rest of our models do, sometimes even worse, because they've created an enormous parameter estimation problem.
So here's another question, and maybe this should be the last one, Xiaowen, as we're getting towards the end of the hour. And it's sort of getting general. What was the basis for selecting BMI? Would that criteria be relevant to modeling beyond water? And that gets into social data and social modeling too.
So the BMI standard is, it's the thinnest possible middleware coupling standard that you could envision. It's really the name of 30 some odd subroutines that your code has to have, and they have to, behave in a certain way. They give you the name of the subroutine. They don't even tell you what's inside the parentheses. So it kind of fits into the parsimony argument that you could go with a much more complex, sophisticated coupling standard, but it's probably going to violate the 2-week target that we have to get people. We could use ESMF from NOAA, and it comes with an enormous code base if you're going to use that model coupling standard that's been optimized and designed for continuum models of the atmosphere. Since we are not running a continuum model, it has a lot of functionality that we just don't need. It's a very complicated coupling standard. So the BMI standard, I think, is the thinnest, simplest, most unimposing standard that anyone in the meeting could think of.
Xiaowen, do you want to keep going, or do you want to call it quits right now?
Yeah, I saw one more question coming from the chat box, Manu Law at Columbia. I think that's a question Fred was alluded to earlier. And the fact that this framework is data-centric provides tons of opportunities of engaging machine learning, deep learning approaches because it's supposed to be data-rich in many ways. And Fred, if you have any further thoughts along those lines, yeah, that was a question from Manu.
That's a great answer, Xiaowen. I agree. There are on the hydrofabric generation, as David was talking about a moment ago, and on the modeling side, there are many opportunities. Machine learning for hydrologic prediction is not the be-all, end-all. It's just another tool in the shed that we can use. But exploring where it's useful, how we can move models from places where it's trained to other situations. Can we use knowledge from the hydrofabric or mine the hydrofabric for clues as to when that's likely, or how it might change the model in some way? Those are all really good questions.
Mm-hmm. Yeah, we are at the top of the hour. I do have also a number of questions, so I'll follow up with you, Fred, offline. But this is a really fantastic talk you've given, Fred. We thank you so much for your time and for sharing your insights. And we've learned, at least I personally learned, there are huge set of potential opportunities and the synergies between this new framework you're leading and mobilizing and what iGuide is pursuing. So looking forward to our further interactions.
I do too. Thank you very much for inviting me. I really appreciate the opportunity to present what we're doing. There are Thanks, everyone.
Thank you. It was wonderful.
Thanks very much. Thanks a lot, Dave. All right, I think.